Hey guys, just checking things out here. We're doing electric potential energy and potential difference. Um, and so we're basically going to be talking about those today. All right, so first off, learning goal is identify the different instance where to use the similarly names. What? Who wrote this? Okay, let's fix this. Identify the different instance where to use the similar named concepts in the selection. Okay, identify the different instances where you need to use the similarly named concepts in this electric potential energy section. So our learning goal, basically, look, a lot of these formulas over here have a similar name: electric potential energy, electric potential difference, electric field strength, right? So they all have similar names. Your goal is to figure out which one is which and when to use which. All right. That's what I was trying to say with this horribly written sentence up here. So your success criteria is that you understand and use the different formulas in this section for determining the motion of particles in electric fields via the energy, right? So we're going to be using kind of more so the energy that the particle has rather than things like the forces applied on it and the kinematics and the accelerations and stuff like that. We're going to be kind of keeping track of the energy and keeping track of the motion through the energy, remembering that like gravitational potential energy that turns into kinetic energy if the particle is allowed to move through the gravitational field freely, like where if you were sort of just let yourself fall in a way, you know what I mean? I'm the particle and I'm in a gravitational field and I just let myself fall by stepping off the edge of a cliff or something, right? Then I freely move, and my gravitational potential energy becomes motion, kinetic energy. And then through an analysis of all of this, you can essentially determine where the object is going to be and when, and stuff like that. It turns out that electric potential energy is the same thing. So gravitational field is, and electric fields, excuse me, are the same. Well, they behave the same in terms of their potential that's built up in the field becomes kinetic energy for the particles that are in the field. Now, the difference is that the field for electric fields, the particle must have charge in order for it to experience the effects of the field. Rather, in a gravitational field, a particle must have mass in order for it to experience the effects of the field. Okay, so that being said, here we've got electric potential energy. This is our first equation, right? And so this is very much like the gravitational potential energy that we talked about in chapter 6. You had some kind of thing that was, maybe a satellite or some sort of rocket ship or something that was moving from closer or further and things like that. The the gravitational potential energy. If you notice, it's the same formula. Okay, it's KQQR, right? The only difference is this one isn't automatically negative. All right, this one will become negative if the signs of the particles are different. Okay, in which case, then you've got attraction. You kind of see what I'm saying? So let's say Q is negative, is a negatively charged particle, and Q2 is a positively charged particle. The overall equation will become negative, and therefore you know that a negatively charged particle and a positively charged particle attract. And so this behaves exactly like the gravitational potential energy formula that we used in the previous section. Whereas if both particles are negative, then you have a repulsion scenario, and this behaves exactly opposite to the equation that we learned in the previous chapter 6. And notice the equation becomes positive in that case, and that's perfect because the opposite behavior in mathematics is a positive thing rather than a negative thing. Okay. Anyway, so that's what we got there. Okay. So not much more to explain, I think, on this equation. It's pretty self-explanatory. K is just your 9 times 10 to the 9. These two guys are the charges of the two particles that are in question, and here's just the distance between them, right? This energy is the energy that the particles currently have at any given moment in time, right? And so as these practice questions unfold, you'll see how they kind of pan out. And so it'll be things like, a particle is here and another particle is here, and how much energy is built up in the system, how much energy is needed to escape. Well, you know that if the uh, if the energy is zero, sorry, oops, at infinity here, the energy is zero, and because these guys would be attracting, okay, and so forth. All right. Conversely, actually, let me mention one other thing. In the case where you have two negatively charged particles, and I push these two guys closer together, these guys wanna repel, okay, and so you're building up a huge amount of energy here, and so in the end, boom, it's gonna want to shoot out there, okay. So we'll keep those in mind as those questions unfold. Let's see, electric potential energy. Maybe this was electric potential energy. This is electric potential. All right. So what is this? This is basically, if you look closely at this thing, it's the same equation as this right here. Okay. And so how does this electric potential behave? Okay, let's give ourselves a particle Q here. And let me just talk about 2 points in space. All right. The electric potential let me just talk about 1 point in space for the time being. The electric potential of this point is essentially, if I were to move 1 coulomb, all right, I wrote my C on the wrong side there, sorry. If I were to move 1 coulomb, okay, from, I suppose, whatever, infinitely far away to this location, that's how much electric potential energy would be required, okay? And now, if I were to move 1 coulomb to here, there would be a different V value, okay? And essentially, what's going on there is the two V values are sort of, they're sort of properties of the space around this charge, but they're in a way a field here, but they're more of like an energy field rather than a force field, okay? So let me repeat this a little bit. This electric potential here, in a way, is kind of like an energy field around a particle Q, all right? And the idea with this is that if I have 2 points in space here, I've got different forces on these guys as well. All right. That's force electric here and force electric here. Okay. If I've got 2 points in space as well, I've got 2 different energy values that I require me to move from one of these locations. Okay. Sorry, from to this location from infinitely far away. Okay, and that's the definition of the electric potential. The actual definition is basically it's the amount of energy that's required to move 1 coulomb, and they're choosing 1 right here just to make it as a standard. 1 coulomb of charge from infinitely far away to a distance r from Q. Okay, so let me repeat that. The voltage is the amount of energy required to move 1 coulomb from infinitely far away to a distance r from the charge Q. All right. Anyway, so that's kind of the idea there. And then the idea is like, okay, well, and then what's the electric potential difference? Well, that's the 2 energy differences between 2 different locations here. So now we can talk about moving from one location to another, all right, back, forth, maybe things like that. So then you have what's called the electric potential difference, okay, which is basically just delta V, all right, and it's the change in energy, all right, from moving from one spot to another. All right. So essentially, the idea with these two things, with this electric potential, it's sort of a property property of space around a particle that allows you to keep track of the energy required or to get to that location. Okay. And let's say the energy to get to this location is 3, and let's say the energy to get to this location is 2, and so therefore the potential difference between those two is 1, right? Because let's say let's say that this one's 2.5, so therefore the potential difference between the electric potential difference between those two is 0.5 in this case, okay? So that brings us to this formula, the electric potential difference, all right? Now, this is the change in electric potential. You can kind of see it. It's right there in the formula, right? It's the change in V, where V is this, okay? So one way of writing this thing is by just basically saying it's KQR final minus KQR initial. Oh, let me write that as well. This is sort of a different way of writing it. Okay, it's the change in energy per coulomb, right? Per 1 coulomb. It's the change in energy. It's how much energy is required to move from one location to another. For a full coulomb, though, remember, this guy is defined as being for a full coulomb. And so you can kind of look at this. If I have 1 coulomb right there, then the potential difference is just equal to the change in energy. Okay. But if I only have half a coulomb, then you have a different scenarios. Okay. So your charge ends up going there. All right. And so therefore you end up being able to adjust your change in energy per amount of coulomb. Okay, so let me explain that again. The idea is that, let's say I take this and I say my delta V times Q is the change in electrical energy. Okay? If I've got 1 coulomb, then it's my delta E is equal to my change in energy. If I've got 2 coulombs, then my delta E, I have twice as much energy. You kind of see what I'm saying? And so I take my delta V, I multiply it by 2, and that's how much energy I've got. Okay? If I've got a half a coulomb only, I take my delta V, I multiply it by a half, and that's how much energy I've got. Okay? Or how much energy, not that I have, but how much energy is required to move from one location to another. All right? Why? And this formula is much more convenient to use than this one in a way, because you're never moving infinitely far away from a location or from a particle to another. You're oftentimes moving from, one location to another. And so rather, it's much more convenient for us to use this formula here. All right. And so basically, that's what we're looking at. All right. Then we also have the field strength here. Okay. The electric field strength. All right. Now, the field strength is KQ1R squared. KQ1R squared. We introduced this at some other time in the past, okay? But I wanted to introduce this formula as well, okay? Or I wanted to talk about this formula as well, because here you've got essentially a potential difference, okay, which it talks about the energy required to move 1 coulomb, remember, from one location to another, all right? That idea, the potential difference, the way of keeping track of the energy, you can actually allow you to figure out the field strength in a uniform field, though. Okay? So this formula here is used for a uniform field, whereas this formula here is used for a non-uniform field. Okay? And that's kind of the idea with those two, right? So you might be saying, well, okay, hold on, you're leaving me a little bit. Okay, so let's explain this a little bit more here. So the uniform field is like this. Remember, there's only one way to create a uniform field in electricity, and that's to have 2 parallel plates that are charged, all right? Now, the idea is that the field strength is the strength in this whole area in here. I'm making the little dots, okay? This is now all uniform. The field strength is the same in there. Well, how do I determine the field strength? Well, it depends on the potential difference between the 2 spaces here. So it's the potential difference between me moving from here to here, all right? And if I maintain the same potential difference, but R, what's R in this case? It's the distance between the plates. If I increase my R, my field strength becomes less, right? Look at this formula closely. Notice what happens if R gets big. If R gets big here, then what happens to this side of the equation? It becomes smaller, because imagine a fraction with a big denominator. Then the other side of the equation becomes smaller. All right, so essentially what's going on here is as I increase R, or if I move these plates away from each other, the field strength becomes less if I maintain the same potential difference or the same energy difference between the two ends of the plates here. And that's pretty much how that goes. What's the way of increasing the field strength? I can increase the field strength by sandwiching the plates in together or decreasing R. I can also increase the field strength by increasing the potential difference or the voltage on the plates themselves, okay? And I just wanted to sort of mention those ones there. All right, and so here's explain the difference between electric potential energy, electric potential, electric field, and electric force. Um, this is the crux of the unit. Okay, and if you're having trouble with this stuff, set up a little appointment or something with me, and I can do my best to try and explain this to you a few different times here. But essentially, I just did explain the difference between them up here. So I'll go ahead and reiterate that. The electric potential energy is the energy between two particles, the energy that they have. If you were to allow the particles then to just sort of be free to move wherever they want. And remember, though, that these particles could slam together due to attractive forces, or they could fly apart due to the fact that they're repelling each other. Okay, so you have to keep in mind that. What's the electric potential? The electric potential is a property of space around a single particle, Q, that's helpful for scientists. It allows scientists to keep track of the energy required to move to that location. Okay. The electric field. The electric field is the field around a particle that allows you to keep track of the force that another particle would experience if in that location. Okay. If it went to that, if it is in that location. And then the electric force is the actual applied force that a particle would feel if it were in a location close enough to other particle. Okay, and so the way that I like to repeat or think about this is the reason why I asked this question here is it allows usually for open up a discussion about this. So what I like to do at this point is sort of draw a box. Okay. So I like to say that the electric potential energy is KQQ over R, whereas the electric force, that wasn't right, is KQQ over R squared. All right. And then you have the electric field, which is KQR squared. And then you've got the electric potential. Okay. And then you've got essentially KQ over R. Right. I kind of like to sort of point this out. It's like this is the, sorry, let me start here. Oh, this is crazy. All right. So this is a crazy thing. This is the field around the particle, force field, the field that you're familiar with. This is the force that an object feels due to the fact that it's in the field. Okay. This is the energy as a property of space. And so this is like a property of space, not outer space, but just any space, could be outer space, around a particle, and it allows you to calculate the force that something would feel, that another particle would feel. This is a property of space around particle Q that allows you to calculate the energy that another particle would experience. And essentially, if you take a close look at these two formulas here, they're just sort of the version of the particle. Look, that thing is right there, and that thing is right there. And so it's like, this is the property of space around a particle. This is a property of space around a particle. This one allows you to keep track of the force. This one allows you to keep track of the energy. And then once another particle actually enters into that space, the actual force that the particle that this new particle feels can be used. You can use this formula to calculate it, and the actual energy that this new particle needs to move around, or gains or loses or whatever, depending on what's going on around the other particle. You use that formula, okay? And so I just try and keep that in mind when you're dealing with all of these things. And then don't forget, you also have this formula up here, which allows you to sort of keep track of the energy change. It's like a bonus formula. This one's a bonus formula that allows you to keep track of the energy differences between moving from one location to another. All right. So if charged particles move from an area with low electric potential to an area with high electric potential, is it possible for its electric potential energy to decrease? Okay. This one's a wild question. Okay, so let's see if I can remember how to do this one. So let's see. If a charged particle moves from an area with a low electric potential to an area with a high electric potential. Okay, so let's build a sort of a system here. Here I've got let's just say we've got a uniform field. No, I'm gonna do this. I'm gonna do this with a single charged particle. All right. I'm gonna do it like this. Let's say I've got a positive particle here. Now, let's get our 1 coulomb. Okay. We're gonna get our 1 coulomb. And we're going to start from infinitely far away. And I'm going to move to here. All right. And then I've got, this is now this out now as an electric potential. All right. Now I'm going to get my coulomb, and I'm going to instead move to here. 1 coulomb. Sorry. Let me write this. This now has a electric potential. We'll call this electric potential 1, and we'll call that electric potential 2. Okay. Question is, which one is higher? Because what I'm trying to do is I'm trying to say if a charged particle moves from an area with a low electric potential to an area with a high electric potential. So what I'm attempting to first do is I'm trying to define 2 areas around a particle, and I'm trying to figure out which one has high electric potential and which one has low electric potential. So what I'm doing is I have to go back to the definition of electric potential here. Electric potential, remember, is this one, and it forces us to use a coulomb, and it forces us to use a coulomb that moves infinitely far away, from infinitely far away to some location in space around a particle. All right. So let's now analyze these 2 V's, this pink V and this green V here. So the question is, how much energy is it required to move to here versus here? Well, I need now let's think about this. This is 1 coulomb. 1 coulomb is positive. The definition of electric potential requires that you use a positive 1 coulomb. All right. So this 1 coulomb is positive, and if I move from infinitely far away to here, it requires a certain amount of energy. Let's call that E. All right. Now, if I move from infinitely far away to here, does it require more energy or less? More. The answer is more energy. So this is now a location of high potential energy. Electric potential. And this is a low electric potential. All right. I've now taken a particle, this one here, and I have defined two areas, an area with a high electric potential and an area with a low electric potential. I've defined those two areas. All right. Now I can begin to start answering the question. So now, if a charged particle moves from an area with a low electric potential, so it moves from here, so it starts here, and then it moves to here, so it ends here. All right. The question is it possible for its potential energy to decrease? Okay. Now, let's take our charged particle and move it from here to here. Wait a minute. I just arbitrarily chose a positive particle. Okay. Let's go with that. I'm just choosing a charged particle and I just arbitrarily made it positive. Okay. So I'm going to go with the fact that this is positive, and then I'll do it also with a negative particle as well, and I'll see. So the question is, if a charged particle, here's my charged particle, moves from an area with low electric potential to an area with high electric potential, is it possible for its electric potential energy to decrease? The answer to the question is finally yes. All right. It's also possible for it to increase, but it's also possible for it to decrease. Okay. So let's now take a look at this. All right. So I've got a positive particle and it moved from here to here. All right. Now remember, I've got my other positive particle here. This positive particle is here and here. Okay. And then in the next example, I'm going to move a negative particle in. Which one has a higher electric potential energy in these two scenarios? This one or this one? Which one has a higher electric potential energy? Turns out this one does. This has a high electric potential energy, and this one has a low electric potential energy. I need more space here. Let me see if I can give us more space. I'm going to pause the video. Okay. I think I got it. Now, there we go. All right, so basically what happened is we moved from a low electric potential energy to a high electric potential energy. So let's now say, why did that happen? Remember that positive particles want to repel. So how much potential energy is here in that blue section that I just highlighted? Okay, well, this blue section here has a low potential energy compared to this one. Because think about this. Imagine this particle is sort of stapled down on the ground over here. Then I've got another positive particle here. To move from here to here, I got to push it in. Imagine I'm taking on my little mouse the arrow is pushing this guy in. It's got to push it in there. So which one has a higher potential energy? This section has a high potential energy. This one has a low potential energy. Because remember what potential energy is. It's the energy that you have built up into the system. And if now allowed to move, if I were to sort of now move my little mouse arrow away, bing, this guy would all of a sudden shoot out that way, like that. Okay. Instead, so basically moving from here to here, I have a low potential energy and I have a high potential energy. When I had a low electric potential and a high electric potential. Okay, so basically, what I'm trying to say with this question is if you move from a low electric potential to a high electric potential, your electric potential energy goes from low to high if your charges have the same sign, right? So basically, your electric potential. I already screwed that up. Electric potential initial. How do I want to write this? Let's see. Basically, there's a direct relationship between your electric potential and your electric potential energy when the charges of the two objects that you're talking about are the same. Whereas there's an inverse relationship between your electric potential and electric potential energy, where if the charges that you're talking about are different. Okay, and so let's talk about that last one there. Imagine taking a negatively charged particle and moving it from here to here. Okay, and which one has a higher potential energy? It's out here. This has a high potential energy. Okay, because basically this negative particle here and this positive particle here want to be together. So it's as if you have a high potential energy as you move towards it, and then imagine pushing it away. It's like the opposite scenario. Okay, and here you have a low potential energy, but we've already established that your electric potential is high here and low, and so you basically have these scenarios here. All right, let me get rid of the ends and the start here. Okay. When V is high or low, your electric potential energy could either decrease or increase. Anyway, I think I've explained that guy a couple of times there. So let's move on to the next question. Example 1, 3 charges are placed at the corners of an equilateral triangle. Oh, another one of these triangle questions. All right, we'll take a look at it. Take a look at the triangle question here. So here's my charges there. We're placed at the corners of the equilateral triangles. And we've got a distance of 0.1 meters, 0.1 meters, and 0.1 meters. Okay. And, oh, look at that. Charge 1 is 1/10 of a microcoulomb. So 0.1 millicoulomb, not a micro. And then this guy is 0.2 millicoulombs. And this guy is negative 0.3 millicoulombs. Find the electric potential energy of the entire system. Okay. Oh, interesting. So this actually is a system of 3 particles. Okay. And they are all sort of sitting here, right? Imagine they're all sort of stapled down. And now all of a sudden, if I were to, if somebody were to come along and remove the staples all at once, bing, 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 cut the staples off, these particles would spring into action until finally they did what they wanted to do, right? And for example, this guy would move towards these both of these positive ones. He would probably move kind of like this towards this one, but he would also want to move towards this one. This guy would move towards this one. This guy would move towards this one, but be repelled. And so it would be like this weird scenario where it's like these guys would kind of go, I don't know, they would do all sorts of weird stuff. But in the end, they would move. They would move. And that the amount of kinetic energy that they would end up getting in total could be calculated by determining the electric potential energy of the entire system. And so to determine the electric potential energy, you're basically all you have to do is add up the electric potential energy of the entire system. And so it's just K Q1 Q2 over R plus K Q1 Q3 over R plus K Q2 Q3 over R. Okay? And so basically it's either way. It's the energy that the thing currently has, all right? The energy that the three particles currently have due to the fact that they're close to each other, all right? And so some of this energy would be positive and others would be negative. So the parts that would be positive would be the positive energy would be the, for example, the relationship where Q1 and Q2. So this one would turn out to be positive, whereas this section and this section would turn out to be negative. Okay. And so part of this energy over here would cancel this energy, but then there would be maybe some more over here. And so you would end up having a total amount of energy of some value, right? And so there's not much to do with this question. You simply just plug those numbers in. Okay. And that's the total built up energy in the entire system. All right. So that could be interpreted in two ways. It's the energy that the particles would have in total if allowed to move. And it's also the energy that was required to end up placing the particles in the locations that they have or that they are in currently. Okay. So determine the electric potential energy at the center. The electric potential at the center. All right. So what we want to do is figure out the electric potential at the center here. All right. The electric potential at the center is simply just V. So KQ over R plus KQ2 over R plus KQ3 over R. And the R is actually, we're going to have to calculate it. It's this one here. All right. It's this distance. And it's the same in all cases, right? So you can calculate that by doing, I don't know, what is the distance between these two guys? So this would be 10, it's a tenth of it. So this is 5 centimeters here. And so that's 30 degrees. Hopefully you're seeing that. I had to draw really small right there. Oh, I erased it again. Wrong stuff. So this is 30 degrees, okay? This is 5 centimeters. So I can figure out this distance here by doing I guess I would use the cosine of 30 would equal the adjacent side, or 5 centimeters, over the hypotenuse, which is question mark, which would be R in this case. R. All right. So there's my R, and that's the same R in all of these cases, okay? This is the R for part B, okay? R, and R. Okay. Now, I would basically just calculate that through, right? That's pretty sweet. And that would be the electric potential at the center of the triangle. All right. And you would get some number. All right. Let's interpret what that number means. That number is the energy required to move 1 coulomb from some location infinitely far away, or I'm infinitely far away over here, to right there. Boom. Infinitely far away where? Over here, over here. It doesn't matter, actually. Just somewhere. If I start way over here, let's say this is infinitely far away, and I move from here to here, it's the energy required to move from right there, from infinitely far away to the center of that triangle would be equal to the answer here if I had a full coulomb while I was trying to move there. Okay. Remember, it's the thing that you're moving from infinitely far away to there is the coulomb. All right, ABC. Let's do part C. Okay. What's part C? Determine the electric potential difference between the center of the triangle and the midpoint of the side between the positive charges. Ooh. All right, so the electric potential difference is... Ooh. Let me get my V back again. All right. The midpoint between... So here, right here. So that would be V final and V initial. Okay. Interesting. So now, basically, my electric potential difference is my change in electric potentials between those. So it's V final between those two locations and V initial. V initial would actually be the answer to this question because I'm moving from the center to the midpoint on the side. But now, basically, just V final, though, would just be KQ1 over R plus KQ2 over R plus KQ3 over R. But the issue, though, is the R's would be different. Like one of the R's would be a half a centimeter. Sorry, it would be 5 centimeters. The other R would be 5 centimeters. And the other R would be this value here, which you would have to figure out. We could figure that out by adding the answer to that previous R, which would be 5 centimeters over 30, cosine 30, plus this little section in here, which that little section in there, you could figure out by using, I suppose, the Pythagorean, because you've already got, you've already got this leg here, and you've got that leg there. So you can use that. You can use the Pythagorean to get that. And so one of these would be, 0.5 centimeters, and the other one would be 0.5 centimeters. 5 centimeters, 5 centimeters, and then the other one would be that new value that I was just defining. Okay, this would be V final, right? And then you would subtract from it V initial, which would be this answer up here. Okay, and you would get some number. Now, conceptually, what is that number? All right, that number is the energy difference between moving a coulomb, 1 coulomb, infinitely far away to here, versus moving a coulomb from infinitely far away to there. Okay? And the difference in those two energies is the potential difference. Okay? So what that allows you to do, it allows you to figure out the energy from moving from one location to another for a full coulomb. Now remember, if you have a half a coulomb, for example, it's only half as much energy. Or if you have a 7 coulombs, it's 7 times more energy. Okay? And so that's what the potential difference is, again, all about. It allows you to keep track of the energy required, energy in and around the space of a charged particle. Okay? Um, it's not an energy in the space. Sorry, I said that wrong. It's the energy required to move from different certain spots in the space. Okay. Field strength. Okay. Last one here is the determine the field strength. And this is going to require a vector addition. So it's field strength 1 plus field strength 2 plus field strength 3. Okay. And I might make a little separate video on this. Well, no, I think I can do it. I got 5 minutes and I got a meeting with somebody. Just ran a little longer. I got long-winded here, guys. Let me see if I can do this. All right. So how do I determine my field strength? Field strength total is field strength 1 plus field strength 2 plus field strength 3. Okay. Wait a minute. What am I trying to do? Determine the field strength in the center of the triangle. Okay. Yeah, that's perfect. Oh, this is pretty easy. And so field strength 1 is just K. Let me go to my triangle here. I'm going to erase all this stuff. So right now I'm trying to figure out the field strength at this particular location. Remember, the field, what would happen to a charged particle if placed here? Well, it would get pushed down by this charged particle. Okay. It would get pushed that way by this charged particle. It would get pulled this way by this charged particle. And if you look closely, this one would be long, right? Because it's this one's a lot stronger, or it's a bigger charge. And this one here, right here, let me erase it. This one here would be the shortest. All right. So essentially what we need to do is we kind of need to just put a coordinate plane here. And what we'll do is we'll say, well, that's 30 degrees. Okay. This is negative 30 degrees. Okay. And this is down here, this one here is negative 90 degrees. All right. And so, therefore, my total field strength is K Q1 over R, right? And the R is that orange R, this one here. It's that value, whatever that is, 5 over cosine 30. Square root of 3 over 2 cosine 30. So you can figure that out. Let's see here. Oh, what's the direction of this? This is Q1, and so that one would be negative 90 plus KQ2 over R, and that's just, again, 5 centimeters over square root of 3 over 2. But Q2, its field strength is coming in at 30 degrees. And plus KQ3 R, and its field strength is coming in at, let's see, negative 30 degrees. And to get this one, you would just end up adding all of these, in a vector addition chart, okay? And I tragically run out of time, but that's more or less how you would do that. And that, the answer to this thing would be the field strength. And so that would be if you were to place a charge there, some charge there, this would be the force that charge would experience, okay? You could use that field strength to determine the force that it would experience, okay?